We're working on example 2 from lecture 3. This is a problem of constant acceleration. It involves two objects called car A and car B. This is a one-dimensional problem, and it should have a lot of interesting steps to make everything work out, to show you what's possible with a one-dimensional constant acceleration problem. It's going to highlight the use of the kinematic equations. So let's read through the problem. Two cars are driving on the freeway. Car A is moving at 33.5 meters per second when it realizes it's closing in on the car in front of it, which is called car B. Car B, in front of car A, is 61 meters away and moving at 29.1 meters per second when car A hits the brakes, decelerating at 1.22 meters per second squared. Car B also notices this, and 1 second later accelerates at 0.914 meters per second squared. The question is there an accident? Do they crash? If not, what is the distance of their closest approach? Okay, so what I want to do here is start by drawing a picture. All right, so let's put some ground in here. All right, so here are going to be our cars. Okay. There we go. That's cars A and B. All right, so here's A, and there is B. Okay. The distance between the cars, all right, when the clock starts, is 61 meters. So we're going to call that x naught. 61.0. I guess we're working with 3 sig figs. All right. Let's add our initial velocities. All right. So we're going to have v naught A and v naught B. Okay. So here is v naught A, and this is v naught B. All right. And certainly they're not the same. And v naught A is larger. That's why if there wasn't the appropriate accelerations, they certainly would crash. Now we're going to find out that if the accelerations in fact make the difference, because car A is moving at 33.5 meters per second initially, whereas car B is only moving at 29.1. And it may not seem like that big of a difference, but 61 meters isn't a lot of ground to cover. Okay, so that's our initial setup. That's our initial information. Okay, so we can call this the initial information. Okay, the equations that we might want to use, so equations of constant acceleration, the so-called kinematic equations. Okay, well, the helpful ones here is we have v, okay, equals v naught. All right, let me just zoom back out. Okay, equals v naught plus at. So that's certainly a helpful equation for us. And when I write v, that's without any subscripts, that's the instantaneous velocity. So really, it's the final velocity. It's the one that's happening at the moment that you're calculating. We also have x equals x naught plus v naught t plus 1/2 at squared. And then lastly, we have v squared equals v naught squared plus 2a x minus x naught. All right, so those are going to be the ones that potentially may be helpful. We might not use all 3 of them, but it's good to kind of collect our equations. And those really are the 3 main equations of kinematics, of constant acceleration motion. All right. And it's also worthwhile to note, and I'll continue to do this, that there's 2 segments to this question. There's what happens in the first second when only car A is decelerating, right, because it hits its brakes and decelerates at 1.22 meters per second squared. And then there's all subsequent time, at which point it continues to decelerate, and car B starts to accelerate. Okay, so we're going to split up the problem into those 2 segments in time. Okay, so consider first second of motion. Okay. So what I'm going to do here is I want to consider what comes out of the first second of motion. You know, what are the final positions of the cars, what are their final velocities, and so on. Okay? So let's do that. So I'm going to write x a, right? So where is car A after 1 second? And to show clearly what's happening with our coordinate system, I'm going to define a couple more things up here in the figure. I want to clearly show that x equals 0 is defined at the center of A. Now, of course, A and B, despite being called cars, are particles here. We don't care about their lengths or anything. And we're defining the positive x direction as basically forward, the direction that both of them are moving. All right, that's positive x. And it's just so important to always define your origin, which is x equals 0, and the location of all your positive axes. In this case, it's 1D, so we only have to worry about the positive direction of x. Okay, so xa, well, that's just going to be x naught a plus v naught a times time plus 1/2 acceleration for a, right? So that's a sub uppercase A, time squared, okay? Well, the t for all of these first equations is all going to be t equals 1 second because we're just finding out what happens after the first second, okay? I also want to find the velocity of a after the first second, so that's going to be v a, and that's going to be v naught a plus a sub a times t, okay? All right, and then I want to do the same thing for B. I know that, well, first let's do the position for B. So the position for B, x B, is just going to equal x naught B plus v naught B times time. And I'll add this third term, but I'm going to quickly show you that it goes away because in the first second, car B, sort of having not noticed what's going on with the potential accident, in the theme of the question, hasn't accelerated. But we'll get to that in just a second. So let's just write this completely. And then VB equals V naught B plus A sub B times time. Okay, so let's, like I said, cancel out the things that are going to be zeros. So in the first second, no acceleration for B. So that's 0. So is that term there. Okay. So now let's just find numerically what's going on after the first second. Okay. So continuing on here, we have then that xa is just going to be 0 plus our 33.5 meters per second times 1 second plus 1/2 times the acceleration of A, which is negative 1.22. Okay, so negative 1.22. Negative 1.22 meters per second squared, and then that's times 1 second squared. Okay, so that will give us the final position of x. Let's go ahead and write that so we can see the exact value. So I'm just plugging in the calculator, 33.5 times 1 plus 0.5 times negative 1.22 times 1 squared, which of course is just 1. Okay, so we have 32.89. Okay, 32.9 meters per second. So here I'll write the rounded value, sticking with the 3 sig figs. I will keep the unrounded value in my calculator, which you always want to do, so you don't have intermediate rounding affecting the your final answer. Okay. All right, so that's the final position after 1 second. Okay, let's do the final velocity after 1 second for car A, and that's just going to be, so 33.5, and you'll see why we need all this in just a moment. So 33.5 plus negative, right, so really a minus, meters per second squared, because they're braking, they're decelerating, times 1 second. Okay, so how fast are they going? Oh, and I made a mistake over here. I wrote 32.9 meters per second. I meant to write meters because, of course, we were solving for distance. So you probably noticed that, and so just caught my mistake there. Okay, so then we got to find the final velocity of A, 33.5 minus 1.22. Okay, because it decelerates for 1 second. So that gives us a final velocity. That's pretty similar numerically. That's probably why I mixed them up. 32.3 meters per second. Right, so it's braked. It's lost exactly 1.22 meters per second of velocity because it was braking at that acceleration rate for 1 second. So you can see how that would work out. Okay, and then we just want to find the final position of B, which is just going to be 61 meters, okay, because it's not at 0. It's at 61 meters based on our coordinate system, plus 29.1 meters per second times 1 second. And that's it, because there's no third term. So then we just go at 61 plus 29.1, and we get 90.1. So 90.1 meters. So we could then already after 1 second, they're closer to each other, right? If we were to consider the distance between them, it's not 61 anymore, right? We would compare this value here with that one, and we'd find that they're less than 60 meters apart at this point. So indeed, they're closing in on each other. Okay. But then everyone starts noticing and braking, but are they braking enough, right, from this point on? That is the question. Okay, so what we're going to do now that we've considered that first second, we'll finish this problem up and consider the second. And it's not, I shouldn't say the second, but rather all subsequent time. We can just run the clock and find out what's happening. Okay? So then consider all time after first second, okay, of motion. Okay, so let's do that. All right, so what we're going to do here, all right, so let me scroll down so you can see it. All right, so consider all time after the first second of motion. So we're going to feed forward the information from the previous part, okay? So that's really going to be the key to what we need to do here. Okay. All right. So what is that going to look like? Well, we're going to have the same sort of equations, and then we want to tackle the question, which was, do they crash? All right. And that's one where we have to really interpret that question and say, okay, what does that look like as a mathematical expression? Okay. Okay. So we want to find their positions now. Okay, so now we're going to take x, a, all right, and that's now going to be equal to I'm going to write it as the same, but what these variables represent has changed. Okay, t squared. Okay, and then I'm going to do the same thing for b. Okay. And I'm not going to worry about solving for final velocities for all the time after 1 second, because the problem doesn't ask for how fast are they going. We assume that they're just going to continue to brake. So we're more interested in the idea of just, do their positions ever match up? And again, I'll show you what that means in just a moment. Okay. All right, so writing the position function for b. Okay, so x naught b plus v naught b times t plus 1/2 a sub b t squared. Okay, so now obviously, like, we don't have a time here. Before it was like, oh, well, we knew what we wanted exactly after 1 second. The time seems kind of like an open question here. How much time? We weren't asked for how long it takes for them to stop, for example. So we're just going to keep t as a variable, and we'll see what that means. But let's plug in what we do know, which will help make sense of all this. Okay, so we know that the initial position after 1 second for car A is the final position we found in the first part, because that was exactly 1 second of running the clock. So that's 32.9 meters, and then the initial position of A is 32.3. So 32.3 meters per second times t plus 1/2. and then negative 1.22 meters per second squared times t squared. Okay, so that's the complete position function for car A for all time after the first second. Let's do it now for car B. All right, so the initial position of car B is 90.1, okay, for the same reasons we're talking about, because it's already been moving for 1 second. And then we have its initial velocity. And its initial velocity, well, notice we never really solved for that up here because it just didn't change. For 1 second, since it was not accelerating or decelerating, it was moving at constant velocity, its velocity remains unchanged. So we're just going to take the 1 out of the problem, and that is 29.1. Okay, so 29.1 meters per second. And now there is a third non-zero term for car B because it's accelerating, because it sees that other car coming towards it and it says, okay, I better hit the gas and move ahead just in case. All right, and so its positive or forward acceleration is 0.914. Okay, so that's 0.914 meters per second squared times t squared. Okay, so now what we're going to do with this information is we're going to set these two position functions equal to each other. Okay, the final position of A, just x sub A, and the final position of B. Because if the two cars do crash, then there should be a time that solves those two position functions being equal to each other. There must be some time at which the two cars are in the same place. Right? Because if it is physically possible for them to be at the same place at the same time, by definition they have crashed. If there is no solution to setting these two equations equal to each other, then we can say no, they don't crash. So essentially what we're going to do is set XA equal to XB, set up, move things around, combine like terms, combine the linear term, combine the constant term, combine the quadratic term, the t squared, and just the constant term, and see if there's a solution to that second order polynomial equation. See if there is an intercept. See if there is a t that satisfies that solution. Okay? All right, so we're going to do that on the next page. Okay? All right, so let's copy these over. All right, so x A, x B, okay? And if the cars crash, then for some value of t, XA must equal XB, because XA and XB are the instantaneous positions of cars A and cars B, respectively. All right, so what does that look like? Well, it looks like 32.9. Okay, and then we'll have, I'll just write it out like this and then just tell you if there's a solution or not. Okay, and then plus 32.3 meters per second times t plus 1/2 times negative 1.22 meters per second squared t squared equals 90.1 meters plus 29.1 meters per second plus 1/2 0.914 meters per second squared times t squared. Okay, so now I got a full solution or a full equation. I just need to see if there is any value of t that satisfies it. Okay, so to do that, I'll just plug this into the calculator and then tell you if there is a solution. Okay. Oh, and I realize here I left off one of the t's because the 29.1 is multiplied by t as the equation states. Okay. All right. So when you plug this whole equation into your calculator, or you combine everything on one side, such as moving the, I could subtract, 32.9 from both sides, and then subtract 32.3t from both sides, and combine the constants and the linear terms and so on. But whatever way you want to do it, and of course the advantage of that would then be to set it up to solve the quadratic equation. But when I plug it into my TI-89 as written, like this, and I ask for the solution, it says false. All right, false. No solution. Thus, the cars do not crash. All right, they do not crash. Okay, so now let's move on to part B, which should just be a natural follow-up because it says, okay, well, they haven't crashed, and of course by asking if it's given away, that I say, okay, well, then how close did they get? What is their closest approach? So let's think about how we would solve that. So what I really want to think about here is a function that describes the gap between them, all right? So we're going to call this a distance function representing gap between the cars. Okay. And I'll call that just f of t, and it's going to be x, b minus xa. Okay. So obviously xb is in front. And so then we can actually take those values. We can then just combine all of our like terms. Okay. So let's do that. Okay. So I've just plugged in the numbers here, done a little bit of math, where I just took 90.1 minus 32.9 to get 57.2, 29.1 minus 32.3 to get negative 3.2, 1/2 of 0.914 plus, because of the negative here, plus 1/2 of 1.22 to get 1.07. Okay, so I've just done that. So we get all the values in one place, and this is our function representing the gap. Okay, well, we need to actually know the time that they're closest, because if you think about it, we can't just say, oh, well, the time when they're closest is maybe once car A comes to a full stop, because it will eventually, right? Car A is continuing to decelerate at 1.22 meters per second squared and will eventually come to a stop. But car A is just speeding up. So car A is just going to continue to get further away after a while. So what we have here is we have a quadratic function, right? We have a second order polynomial that's going to have some minimum value. So in order to find the minimum value of the position function that represents the gap between the cars, well, we have to take its first derivative and set that first derivative equal to 0, because then we will find the value of t that represents an extrema. Now here we're going to assume that our extrema is a minimum, because there's really it can't really be anything else, because it's just a parabolic function, and we know that it's facing upwards. So we're just going to solve for take the derivative of our function here, set it equal to 0, and solve for t. Okay, so let's do that. So df of t differentiated with respect to time. Okay, so that's just going to look like 0, because the constant just becomes 0, minus 3.2, and then plus 2.14 times time. Okay, and we set that equal to 0, and then solve for t. Okay, so then t in this case, I'll just do this in the calculator, it's going to be 3.2 divided by 2.14. All right, I get 1.50. So t equals 1.50 seconds. Okay, so this value of time corresponds to smallest gap. Okay, because that's what we've done. We found the minima. Okay, minima. Okay. All right, so now finally, then we can plug that time back into our gap function. So then to find minimum distance between cars, we're just going to take f of 1.50 seconds. Okay. And what that's going to look like, I'll bring that down here. All right, we'll go back to our gap function, this one right here. And we're going to have 57.2 meters minus 3.2 meters per second times 1.50 seconds, and then plus 1.07 meters per second squared times 1.50 seconds squared. Okay? All right. So what do we get? Minus 3.2 times 1.5. Just plug in everything in the calculator. Plus 1.07 times 1.5 squared. Okay? All right. So I get a closest approach of 54.8 meters. So they never even come close to crashing. I mean, come on, they started at like 60, so they were very responsive. Let me bring the values so you can see them here. The cars really responded quickly to their approaching each other, or maybe they were over worried. But whatever, we ran the numbers. We used some interesting techniques here of, for example, finding the minima of the gap function between the cars, and carefully considering what happened in the first second versus what happened in the subsequent time. All right, thank you.